Suppose we have the function y equals 10 to the power of 1 minus x squared, and we would like to differentiate this function. There are two approaches I will show here. There is a shortcut for handling exponential functions with a base other than e. If you have not yet read that part in the textbook, or you think it's possible that you might forget that rule at some point, we can do this directly. So first I'll do it directly, and then I'll show how we can apply this just using the shortcut. So suppose we didn't know anything about any special forms here, and we just had to deal with this. And we want to find the derivative dy by dx. Well, the problem is this function is an exponential function base 10. And in previous sections, we looked at the derivatives of exponential functions base e, but not base 10. So before we actually compute the derivative, we will need to do a little bit of algebraic manipulation. So let's focus in on this 10 and think about a way that we could maybe write that as e to a power. Well, that would be e raised to the power of the natural log of 10, right? E raised to the power of the natural log of 10 would simplify down to just 10. So what I have in parentheses here is just equal to 10, so we have that thing to the power of 1 minus x squared. So we look at this, and now if you remember your exponential properties, log 10 is a constant, so if e to a power, that is e raised to the power of the product of the powers, e to the log 10 times, parentheses, times 1 minus x squared. Okay? So now when we take the derivative, we're taking the derivative of an exponential function, a natural exponential function, so that is e to that power, times, the chain rule tells us we now have to multiply this by the derivative of that exponent. Well, the first part is the constant natural log of 10, so that passes through just fine. And then we have to multiply by the derivative of this, the 1 minus x squared. The derivative of 1 is 0, so then we have minus 2x. So we see that we have, let's bring that negative 2x up to the front. We'll leave the log 10 at the end for reasons of clarity. E to the log 10, we can just reverse what we did up here. E to the log 10 simplifies down to 10. So that is 10 to the power of 1 minus x squared times the natural log of 10. Right? We can put in some multiplication dots if we wish to make that a little bit easier to parse. Negative 2x times 10 to the power of 1 minus x squared times the natural log of 10. So that's one way that we can do this thing. Now, this was a little bit unpleasant. There's sort of a bit of a rigmarole here. So the second approach, in the second subsection of the textbook, they work through something of the general form b to the x. And they basically go through those steps that I just did where we write this as e to the power of the natural log of b and work through, and we find that the derivative of b to the x for a constant b, not a function, but a constant value b, is b to the x times the natural log of b. Okay. And if you think about this, this even works, this works for any valid base b. Suppose b is actually e, so we have a natural exponential function. We would have e to the x times the natural log of e, but the natural log of e is just 1, so that reduces down to e to the x. And there are no problems there, right? So this is just a generalization of the special case. E is the base where the derivative of the exponential function is itself. Any other base, we have that scaling factor to worry about, the natural log of that base, because that won't be 1, so we'll have to figure out what that is. Well, we can take this now as just a derivative rule. So returning to this original function, if we remember this rule, we can say, all right, so if y equals 10 to the power of 1 minus x squared, then dy by dx would be 10 to the 1 minus x squared times the natural log of 10. This is the applying that rule. But now we still have to apply the chain rule and multiply by the derivative of the exponent. The derivative of 1 is 0, negative 2x. So we get basically the same thing, but with less algebraic manipulation if we have just sort of remembered this formula. And again, we would still want to bring that negative 2x up front to make that a little bit easier to read, probably. But we'll get the same result with less work if we happen to remember this formula. So I recommend trying to add that to your mental list of known derivative rules. Practice with that, get used to how it works, because it can save you some trouble and some time and some effort. But if you ever do forget it, there is this technique by which we could always manipulate the expression, force it into a natural exponential, and just apply the rules that we know. So, you can always fall back to that if you need to.